Hi, I'm Jan Ozer. I'm meeting today with Arsalan Zafar, CTO and co-founder of DeepRender, an AI-based codec developer, and Sebastjan Cizel, who's head of engineering at DeepRender. We're here to discuss the progress DeepRender has made over the last few months with their codec to see how it compares to other AI-based codecs and other traditional codecs like HEVC, AV1, and VP9. And we're also going to see a demonstration of the codec encoding and decoding in FFmpeg and decoding in VLC, which is pretty exciting because I've never seen an AI-based codec work up to this point. Read plenty of white papers, but just haven't seen one in the world. So thanks for joining me, Arsalan and Sebastjan.
Thanks for having us.
Thanks, Dan.
My pleasure. So in terms of flow for this video, Arsalan's going to start us with a brief discussion. He's going to show the comparisons that I talked about a moment ago, and then Sebastjan will run through the demo, and then we'll circle back and we'll do a quick Q&A about what we saw and where the technology is and how it's being and how it would be deployed, hopefully in the near future. So Arsalan, why don't you kick it off with your presentation?
Yes, of course. DeepRender's built the world's first AI codec, and more specifically, DeepRender's built the world's first and only production-grade end-to-end AI codec, and it's running in real time on today's hardware. Not only is it the world's first AI codec, but it's an entirely new paradigm which allows us to deliver video quality and provide unprecedented improvements over time. Let's have a bit of a look at what I mean by AI codecs. So there's the old paradigm and the new paradigm. In the old paradigm, we get an input video that undergoes macro blocking and DC transform to produce compressed data. In the new AI-based paradigm, an input video goes through a neural network to produce an output data. The compressed data in the old paradigm then goes through inverse DCT to produce an output video. In the new AI-based paradigm, the compressed data goes through a neural network to produce an output video. And as you can see in this new AI-based paradigm, we are purely using AI models and not relying on any components from the old paradigm. Touching a bit on performance that we're seeing with our codec, we're going to talk a bit about the BD rate curves. And we produce some BD rate curves of visual perception on the AOM C2C V2 dataset, which is a commonly used dataset in the compression world. And we compared the DeepRender codec with AV1, HEVC, and VP9 on some standardized command strings. And what we're seeing is roughly a 40% improvement over AV1 with the DeepRender codec when it comes to visual quality. We also looked at a diverse dataset, and here we wanted to include video conferencing data, which are talking heads, gaming, animation, cinematic, and mobile recorded data. And again, we compared ourselves to AV1, HEVC, and VP9 on visual quality. And as we can see here, DeepRender can also provide significant gains, giving up to a 50% improvement. So for the same quality, we're getting roughly half the file size. And this is what's really enabled by this new paradigm of purely being an AI-based codec.
Can you go into some of the numbers that that you have there and tell us about the presets that we use for AV1, HEVC, and VP9, and also how that reflected in encoding time?
Yeah.
That's good. Yeah, I can jump in on this front. Yeah, so I'll start off by saying so in terms of the encoders that we used for this comparison, for AV1 we used the SVT AV1 encoder. For HEVC we used the X265 encoder, and for VP9 we used the libx VP9 encoder. And we ran very extensive data generation, like reference data generation runs to try to figure out which presets or which encoding commands most closely align with sort of the performance expectation and our use case. So I have to give a bit of context. We are generally benchmarking in the real-time regime. So we are looking at the real-time codec performance. So additionally, one of the key constraints is that we are currently exposing the constant quantization parameter rate control mode. So we're trying to equalize the rate controls as much as we can between encoders. And all of these factors basically are factored in into the exact command string that we choose. So in terms of SVT AV1, we collaborated with a developer of SVT AV1 and landed on using preset 7 in our benchmarking. So on the X265, we ended up using a preset medium, and for VP9, we tried as best we could to consolidate this rate control and the real-time use case, which for VP9, for libx VP9, is not sort of the preferred mode of configuration. But we ended up using the CPU use 4, so speed 4, in the real-time regime for libx VP9.
Okay, thank you.
Thanks for that. Yeah, so that's a bit on the performance. Yeah, just to reiterate, because we moved from the traditional DCT microblocking paradigm to a purely neural network-based paradigm, we're seeing significant improvements today, and we're continuing to see significant improvements in the future. We will continue to see significant improvements in the future. A bit about the encode decode speed of Deep Render's AI codec. So we ran some tests on an M4 user device, an end user device, across several resolutions. So as you can see, Deep Render on encode can provide roughly 22 FPS currently with our latest release. On decode, we can hit up to 70 FPS, which is very nice. So you can play your 1080p and 30 FPS streams. And the last column is BDT. BDT is battery drain tests, or battery drain time, where we essentially start off the device at 100%, play back at 1080p 30 FPS stream until the battery dries out, and measure the time for that. The previous encode and decode numbers are also at a 1080p, of course, resolution. You can also see at 720p and 540 that the numbers also scale very well. We think these are extremely strong starting numbers, so it's a great starting point for AI-based codecs, and we expect significant improvements, as with all codecs, which start off relatively inefficient and become efficient over time. We expect significant improvements over the next 12 months, and that's composed of improvements to the architecture and the software stack, as well as hardware improvements in the NPU. We have encoding and decoding binaries available for testing for those that are interested.
Okay, a question on the MacBook Pro. I mean, Apple's been way far ahead with getting NPUs in a lot of their devices, including both laptops and smartphones. Are you using the NPU for encoding on this on these tests?
Yeah, we are, and because our encoder and decoder are composed of purely machine learning operations and machine learning primitives such as convolutions and nonlinearities, we need to use, or we rely heavily on, neural processing units, or ANEs, that are becoming quite prolific and are in a lot of the devices, not just in Apple, but Qualcomm, MediaTek, and Intel are also, and Google are also have them in most of the devices, and are continued to improve those. There's billions of these devices with NPUs already in existence, and that's scaling quite rapidly. And if we don't use an NPU, then these numbers look significantly worse, since the NPU for us is kind of like a specialized device, hardware for our codec.
Okay. Just jumping in there, it is also possible to run, of course, on the GPU, and we have done so before. We have been running on consumer-grade GPUs as well, and we can reach reasonable encoding speeds, reasonable encoding and decoding speeds closing into 30 FPS on GPUs as well. But obviously, A&Es are where we thrive and where we want to run our models.
Okay.
Awesome, thanks. I briefly also want to touch on how Deep Render's AI codec compares to other AI-based codec research that some other entities have been working on. And a lot of this work on AI-based codecs outside of Deep Render has mainly been happening in academia. And we'll use this compression efficiency and low complexity on Y and X axis respectively to kind of map this out. So where you ideally want to be is on that top right-hand corner where you have extremely high compression efficiency and low complexity, so you can get that wide device coverage. That's where Deep Render currently lies compared to some of the other players that have looked at it. So a lot of research, some of the research coming from Microsoft or WaveOne or Qualcomm, who have attempted AI-based codecs. What we find that is that those systems are either too complex or not performant enough. So, for example, Microsoft's research at DCVC is about 2 orders of magnitude more complex than Deep Render, whereas Qualcomm, which is comparable but still about 2 to 3 times worse in complexity, is significantly worse in compression performance, being about a few 100% worse than AV1. And Deep Render is the only codec that can provide both high compression efficiency and low complexity at the same time. And it's what we've been thriving to do for the last few years. Here's some more a more detailed breakdown on these numbers and compression performance.
What do these numbers mean? I mean, did you actually implement these and test them, or are these derived numbers from some of the white papers, or what are we looking at here?
It's a bit of a mix. So one fundamental limitation when trying to objectively evaluate all of these architecture is the availability of reliable data or availability of the reference information that you need to be able to implement these yourself. So some models here are better than others, but fundamentally our approach here was we try to extract as much as we could in terms of both runtime and compression performance numbers from what papers reported, so taking the results at face value. And where possible, we also attempted to implement and actually measure the performance ourselves.
Okay.
So yeah, so what we're claiming here is very closely aligned with what the papers actually self-report.
I mean, it's almost impossible to test these on the same platform because a lot of these require GPUs to be working, and you guys are working on NPUs, which are more common and have a lot less power than the GPU. So
exactly, yeah, that's right. And I mean, in addition to that, there is the whole space of the GPUs that these papers run on. And there are some papers, for example, like the WaveOne paper is from a couple of years ago, and they run on one set of GPUs, I believe Titan 5s, whereas DCVCFM is a more recent paper, and they are using more like stronger hardware as well. Qualcomm, on the other hand, is the only other codec so far that has been run on a mobile platform, but it's on a different platform as well. It's on a Qualcomm, unsurprisingly.
Right. Okay, got it.
Awesome. Yeah, so just to reiterate, getting both high compression efficiency and low complexity so you can actually have a production-ready codec is being Deep Render's aim. I'd also like to touch on some other disruption AI-based codecs cause. So since we're moving entirely to a new paradigm where we're purely AI-based, there are some other changes that happen in the ecosystem, and the old way or the previous method of developing codecs it can be disrupted. And so if you look at the old supply chain, it was composed of multiple entities responsible for critical components. So you had research labs pouring in thousands of ideas, which then went through a selection process, which was always interesting. And then the standard bodies come in to standardize everything, and then that needs to be collaborated with. There needs to be collaboration with the silicon industry to have the hardware rollouts and the chips and make sure that's fully optimized. Then the patent firms get involved, and then there's pricing, and then there's patent pools, and then eventually that ends up in a user. But because it's kind of a bit fragmented and these parties not necessarily the best of friends, what you get is essentially the user suffers because it takes a significantly long time for us to push codecs to get codecs out, and it doesn't need to be the case. Codecs don't have to take so long to develop. So the ecosystem is super fragmented. But under this new paradigm of an AI-based codec, that doesn't need to be the case anymore. And for example, for deep render, we do everything that you saw on the previous slide in-house. So we do the AI codec research, we generate the ideas, we turn them into a product with the AI engineering and hardware integration across multiple platforms. And since we run on commodity hardware, we're essentially converting these codecs into software-based codecs. So it doesn't need to be a hardware-dependent industry anymore. Then we have an IP team that locks down the IP, and essentially a commercial team which releases this. So the user benefits from this, since we go through rapid iterations of new codecs coming out really fast, and the user just, from their perspective, sees significant improvements in the codec, and everyone benefits. And now you just essentially go to one entity and get the best codecs. So just to reiterate everything I mentioned so far, what AI-based codecs and deep render are promising are the best-in-class compression performance, best-in-class compute complexity, real-time runtime on encode, and acceptable and extremely strong early battery drain numbers. So I hope that's given you a nice overview of where AI-based codecs and where deep render codecs stand today. We'd like to show you the world's first AI codec in FFmpeg, and we'll also like to show you the world's first codec in VLC. To do this, I'll hand over to Seb, who'll run you through some demos of this.
I guess I'll start with a little bit of motivation as to why we actually went down this route of developing the FFmpeg and VLC integrations. Point number one here is that video codecs are ubiquitous, and they're a very important part of the tech ecosystem, and as such have developed a fairly extensive evaluation and application stacks. And being able to integrate with commonly used tools such as FFmpeg and VLC gives us the ability to sort of seamlessly integrate into these stacks so that we are able to directly compare our AI-based codec against all of the other codecs that exist out there. But even more fundamentally, what we're trying to build here is a product. So a lot of AI-based compression now only exists in the sphere of research, because AI-based workloads are still mainly GPU bound, not consumer GPU bound, very strong NVIDIA, thousands of dollars GPU bound. And what we set out from the very start is to build an AI codec that can run on commodity hardware, that can run on laptops, that can run on people's phones. And being able to integrate into an application like VLC unlocks this possibility for us. We are able to suddenly run our codec within this application stack, and we're able to share it with other people and show that we can actually run. So what I want to do is I want to bring up my screen. So I will start this demo by going through the motions of encoding a video and decoding a video using FFmpeg. I will be running on an M4 MacBook Pro. So this is the baseline MacBook Pro with the M4 chip. Let me start off with the encode demo. So I prepared a small demo folder here. So let's jump to the terminal and look what's inside it. So you'll notice crucially that there is an FFmpeg binary sitting inside this demo folder, as well as deeprender's VLC application. In addition to that, we also have the FFprobe application that will allow us to look under the hood of deeprender's MP4 containers and examine their metadata. So the clip that we'll be using for the encoding and decoding comes from Netflix Open Content Dataset, and it's a food market clip that we've modified to be at 1080p resolution, 30 FPS, and 8-bit. Before we jump into the encode itself, we can quickly examine and look at how it differs from the standard FFmpeg. The users of FFmpeg will quickly note that the banner that we see right here is quite a bit different to the standard banner that you're used to with FFmpeg. Most crucially, the things that we need to include are the frameworks and libraries that allow our codec to leverage the neural accelerator hardware that's available in this MacBook Pro. Most importantly, out of those is the Core ML framework, you can see right here, that allows our models to run on the neural engine, as well as the Metal framework that allows us to utilize some custom operations on the GPU. Let's move to the encode bit. So let's start by looking at the encode command that we'll be using. The encode command is pretty simple. So we will be using the local FFmpeg binary, and we will be encoding the Netflix food market clip using the deeprender codec, so the deeprender encoder. The main mode of rate control that we currently provide is the so-called constant quantization parameter rate control. So we will be setting the quantization parameter to 35. We will be writing the deeprender bit streams into an MP4 container, which is the default container that we use in our integrations. So let's start encoding this video. So you'll immediately notice that we are indeed encoding with the deeprender encoder and that we're realizing about 20 FPS. I will note, because we are currently recording the screen, the FPS may be a little bit more volatile than normal. So we have successfully finished the encode, and before we move on to decode, we can examine the MP4 file that we've just generated to see the metadata contained inside it. So for that, we will use FFprobe, and we will provide the encoded video to FFprobe. So I want to highlight here that you can indeed see that we use the deeprender encoder, and of course that the metadata shows that we are expecting the deeprender decoder on the other side. So now we can move towards the decode portion. So let's briefly look at the decode command as well. Decode command is also quite simple. Again, we're using the local FFmpeg binary and passing the MP4 that we have just generated containing the deeprender's bitstream. We will be decoding that bitstream back into a raw Y4M file. Again, you can see we are using the deeprender decoder, and we are able to realize about 64 FPS running on this MacBook Pro. So that's decoding the bitstream at 64 frames per second. So if we look at the demo folder now, we will notice that we indeed have the bitstream or the MP4 file that we've generated, as well as the decoded video in the Y4M file. So for the final step, we can move towards a different window and navigate to the demo directory here. And we will now play back the deeprender encoded video using the VLC application. So you'll notice this is the same folder that we have just been viewing inside the terminal. And here is the Deep Render VLC application. So to play back this video, it's as simple as opening this MP4 file with the custom VLC application. And that's it. So you will notice that right now we are playing back the Deep Render's encoded video using the Deep Render decoder built in to the VLC application in real time. So in summary, what I've just showed you is not only the world's first AI-based video codec, but world's first integrations into FFmpeg and VLC player that are running on edge hardware on a MacBook in real time, capable of encoding at 20 FPS and decoding at over 60 FPS.
Okay, thanks for that, Sebastjan. Let's go through some questions that I have on the implementation side. So what happened before all this? Describe the training process to get to this point.
Of course, yeah. So in terms of our model training, we have a pretty extensive research team and the engineering team that are training basically tens or hundreds of new models every week. So we basically have an in-house training library, in-house training data set that consists of terabytes of as high quality content as we can get it. And we are continuously training and improving our networks to try to squeeze as much compression performance as we can. So in terms of what that actually entails, so we try to iterate on models quite quickly, but basically every 2 months, we have a new internal release of the model, and we expect roughly 15 to 20% improvement on the, every 2 to 4 months. And these then get integrated into the downstream software stack.
So talking about that software stack, in a few weeks, I'll be testing your version of FFmpeg. What am I going to need to run that? I know the hardware side. I'm going to need a machine with an NPU, probably a Mac of some type. But what about the model side? How do you transfer all that technology? Is there this huge bunch of files I have to get, or is that kind of built into a smaller executable type thing?
Right, that's a great question. So in terms of models, we can basically ship them with the binary. So models, depending on the platform, exist generally as an asset. So that there exists a model sort of file that gets bundled and shipped with the binaries that we will deliver to you. So from the user's perspective, it's not much different than your normal FFmpeg. So somewhere in the background, there exists a collection of models that leverage the system-wide installed libraries to be able to run on the relevant hardware.
Okay, and give me an estimate of the file size. Are they 1 meg, 1 gig, 1 terabyte? I mean, how big are the models?
So our current total binary size is at around 150 megabytes, but that involves a few different models as part of the binary, right? So there are some limitations in the current AI ecosystem that require models to be statically compiled to particular shapes. This is not an intrinsic limitation, but this is just like the current state of things. So that's why we're shipping a couple of different models to accommodate various modes of operation.
Okay. Yeah. I mean, at the current stage, the model size and the binary size is not really something we've optimized for. So we've kind of produced something that can be tested and used. Rolling this out to applications worldwide with 150 MB binary, you can't really do that. There are limitations on that. We've shown internally that you can actually get this down to a few hundred kilobytes. And there are methods where when you update an application that's running this codec, you don't have to ship the weights along with it. They can be bought, downloaded later as assets and so on. So in actuality, when you embed this, it's only the source code and the structure of the layers, and it can fit into a few hundred kilobytes when rolled out widespread.
Okay. Well, you've kind of demonstrated the quality and also the playability, pretty impressive on an M4. What does that translate to into target markets? Because you do need the NPU, and NPUs are, they are in some places and they're not in others. How do you see this rolling out in terms of markets that you can penetrate in the short term and then in the middle term and long term?
Yeah. Depending on the hardware manufacturer, NPUs have been around. So there was an NPU in the iPhone 8, and it just got significantly better and better. So iPhone 12 or iPhone is roughly where we would say our codec will start to work in a reasonable place. There's, I think, 10% of people update every year, so we expect pretty soon, basically, most people are using devices that we can run on. So from an Apple perspective, most of the mobile devices, laptops, are covered. That a similar story applies for Qualcomm and MediaTek and so on. And generally, we work better on the latest flagship machines. And as you go down to the lower tier devices, as the NPUs get smaller, there are consequences of that. So you either have to use a slightly lower resolution or a slightly lighter model, and maybe compromise a bit on the performance. So you have to make that trade-off. Yeah, so that's roughly so rollout. Depending on what the customer would like to do, this would be rolled out on the flagship devices first, where generally the higher resolutions are produced and consumed, and then there will be a staircase down to the lower ends.
Okay. What about the smart TV and the computer markets?
Computer markets, when it comes to Mac, that's totally fine. Intel has been recently making a massive push, so they have A&Es that are ramping up pretty fast. So I think that's great. Smart TVs are generally a bit slower to make progress, but they're also starting to introduce NPUs. So we're looking forward to integrating it there, but we expect that to be one of the last markets.
Okay. Will there be dongles that support NPUs that you can use as opposed to, the native smart TV technology itself?
Yeah, very likely. So you can take the Apple TV box that had an NPU that has and then that NPU will get stronger. So that's pretty great. NPU processing is very likely on the roadmap for most of the dongle providers.
Okay. Okay, listen, this has been great. I appreciate you taking the time. And, I look forward to playing with FFmpeg and Deep Render myself in the near term.
Awesome. Thanks for having us again, Chan.
Thanks.